This is Gail Kovac with Gresham Barlow School District, Summer School, High School Credit Recovery, and Geometry Learning Target number 7. I can use side similarity, angle similarity, and side similarity to determine if triangles are similar. So congruent means the triangles or the shapes are exactly the same. They're the same size, they have the same angle measures, the same side lengths. Similar, in the other hand, means that they have been transformed through a process of dilation. That creates angles that are exactly the same. The side lengths might be different because one triangle or shape is going to be larger or smaller than the other one. So they're not going to be deformed, so the angle measures are going to be the same, but the side lengths are going to follow the same scale factor. So the entire triangle or shape will be twice as big or half as big or 7 times as big or whatever it is. Now, if we happen to have any of these bits of information that we already know about triangles specifically that match or follow the same scale factor, then we can already guarantee that the triangles will be similar. We don't have to check for third angle or third side or something like that. So let me show you what I mean by that. So let's see what we've got over here in the first set of triangles. I've got BAC and GHF. I have been given no marks that the angles match, unlike the next example here where I have some red marks, right? So I don't have any information about matching angles. So likely I'm not going to be looking for angle similarity or side angle side. I also can't use triangle sum theorem here because I have no information to go on. So I am most likely here going to be looking for side similarity. Now you might think, well, none of the sides match. So yeah, they're not congruent because none of the sides perfectly match. But if all 3 pairs of sides, corresponding sides, follow the same scale factor, then those triangles will be perfectly similar. So let's take a look here. And I like to, because you can also tell that these triangles have been twisted around a little bit, so they're not oriented in the exact same fashion. So it's kind of hard to tell like which one matches to which, right? So I do smalls first, then mediums, and then bigs. So in my triangle BAC, my smallest side length here is 48 across the bottom. My smallest side length in GHF is this one. The 8 is the smallest one out of the 3. So I would like to know from small to big, how many times bigger is that? What is the scale factor here? What do you multiply to 8 in order to get 48 as an answer? And I like to go backwards against the arrow and divide to figure out what that is. If you do 48 divided by 8 in your calculator, you're going to get 6. So this side length of 48 is 6 times bigger than my 8 here. I need to make sure that both other pairs of sides, the medium ones and the big ones, they also follow that same scale factor of 6. So now let's go to the medium side. So for 8, 14, and 12, 12 is my middle value. That's the second biggest number. And that's going to correspond to 72 here, because that's my middle number of 48, 72, and 84. So I need to now figure out what my scale factor is from 12 to 72. Is it also 6? Let's check. I'm going to go backwards and divide. 72 divided by 12. Sure enough, that's 6. Multiplying 12 times 6 does get you 72. So far, so good. We've got 2 pairs of side lengths that match with their scale factors. We're going to try the third one over here. My largest on the triangle on the right is 14. I'm going to see if that scale factor to the 84 is also 6 or not. As long as all three of them match with their scale factor, then we can say that those triangles are in fact similar. So to go from 14 to 84, I wonder what that scale factor is. What do you multiply to 14 to get 84 as an answer? Let me go backwards and divide. 84 divided by 14. Sure enough, yes, that is times by 6. 14 times 6 also equals 84. So we have a multiplier of 6 for the smallest sides, a multiplier of 6 for the medium side, and this exact same thing for the largest side. So in this case, we're going to say, yes, these triangles are the exact same shape, but just different sizes, and that's by side, 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 similarity. We add that little similarity symbol right there, that little squiggle, to show that it's not side, side, side for congruency, not three pairs of sides matching exactly, but similarly, they are the same ratio to each other. This triangle on the left, although the image does not look nearly correct, it is not to scale. This triangle on the left, its side lengths are 6 times bigger than the one on the right. In fact, triangles that are congruent by side, side, side congruency, the scale factor is 1. It's times by 1. It's just the exact same ratio, the same number. All right, so let's try the second set of triangles here. Let's see what I've got so far. I'm looking for matching angle measures in this case because I don't have any side lengths at all. I can't check for any side lengths, so I need to see if I have any angles that match. So I can't check ratios for side, side, side. So both of these are out. What I'm looking for is, do I have two pairs of angles that match or not? So far I see, okay, in this bottom triangle here, I see this, that has 1 mark. And at the top, oh, no other marks of 1. Oh, okay, well, no match there. In the top triangle, I see a mark of 2. And in the bottom, oh, no marks of 2. Okay, no matches so far. I do have a mark of 3, though, at the top here. Does that match with any at the bottom? Well, shoot, there's no mark of 3 anywhere either. I don't know that I have any angles matching. But in fact, if you remember the vertical angle theorem, angles that are across from each other in this little bow tie fashion have to be congruent. So in fact, I do have 2 angles that match. This one here must be the same measurement in degrees as this one down here. And I'll just color it in so you don't think it matches with that angle B at the bottom there. So these two have to match. So I've got 1 pair of angles that match. And that's all I've got. I can't check any ratios for corresponding sides. I don't have any marks that indicated anything matches. I don't know what's going on with angle C down there. Maybe it does match with angle T, but I'm thinking it might not, especially since U and B are different angles. Those would have to be the same. Yeah, in this case, we got a big fat no. These most likely are not similar because we just don't have enough information. All we've got is 1 pair of matching angles, and that is not enough information to say for sure that those triangles have to be similar. So now we're going to try one more example over here on the right. I've got 2 separated triangles. I got WUV and HFG. Let's see what information we have here so far. It looks like I do have a matching angle. Now, in this case, it's not given to me as a mark. It is actually given to me in its measurement. So far, I know that I do have a pair of angles that match. They're both 76. Let's see. I don't have any other angles here given. And I can't solve for any missing angles because I'm missing 2 out of 3 for the triangle sum theorem. So unfortunately, that doesn't help so much. But this relationship also has side length, so I can check the ratios of some side lengths here. So let me do small to small and then big to big. So in the triangle on the top, I've got this side length of 9, and that should correspond to this side length here of 21. That's the smallest out of the two. So let me see now, and it looks like this thing's been crazy twisted around. What is the scale factor from 9 to 21? How many times bigger is 21 than 9? I'm going to go backwards and divide 21 divided by 9. That is 2 1/3. That's 2.3 repeating as a decimal, or 2 1/3. 2 1/3. All right, so far I know that this side length, HF, is 2 1/3 times bigger than the side length UW. I wonder if that same thing is true for this long side here, UV, and this side length here, GF. So let's see here. My scale factor from 18 to 42. Let's see how many times bigger that is. I wonder if that's also 2 1/3. So 18 times what equals 42? I'm going to go backwards and divide 42 divided by 18, and I get 2 1/3. All right, so that's 2.3 repeating. That's 2 1/3. So in fact, here I do also have, let's see, I've also got 2 pairs of sides that correspond. Now, I'm specifically now going to be checking this. I want to make sure that I've got 2 pairs of sides that correspond and have the same scale factor. We just checked that, we do. And I also need to make sure that the angle that matches is in between those. If the angle was off to the side, then it would be ASS similarity. And we talked in the last video about ASS and how that one just don't work. So let me see here. I've got a side, an angle, and then a side. I've got a side, an angle, and then a side. Yes, in fact, this is side, angle, side similarity. So side, angle, side similarity. Those two triangles must be similar to each other, which means that third corresponding side, the big one, VW and GH, they're also going to follow that scale factor of 2 1/3. And whatever angle G is, it's going to match with angle V. And whatever angle W is, it's going to match with the angle H. I don't even need to check everything else. My theorem says, yes, that's enough information. Those triangles for sure are similar. So just make sure that you are checking that this side lengths not match, because that's for congruency, but they follow the same scale factor. So that's what we are looking for here. Like in this one, we had side, angle, and then side similarity. We checked to make sure it was in between.